All right, my friends. So let's take a look at problem 8 here. A lot of people are asking about this one. It says a tank contains 50 liters of oil at time t equals 4 hours. Oil is being pumped into the tank at a rate of R of t, where R of t is measured in liters per hour and t is measured in hours. Select the values of R of t. Selected values of R of t are given in the table above. Using a right-Riemann sum with 3 subintervals and data from the table, what is the approximation of the number of liters of oil that are in the tank at time t equals 15 hours? Okay, this is definitely the kind of problem until you practiced it that makes you just want to skip it. But let's practice it because I don't think this will be too bad, and it practices some moves that would be good to have for other problems anyway. So one thing that I tend to do, especially when I'm explaining to other people, is thank the College Board for their choice of notation, but really tended to say no thank you. So I don't like it when they use uppercase letters for rates. I think it's rude. So personally, I would change the notation. So instead of R of t, what I would do for this one is I would decide that I'm going to let V basically be assigned to be the volume of oil in the tank. And then the rate of change of the amount of oil in the tank with respect to time, that is like that's basically what they are having big R of t represent. So just a note, like that would be their R of t. Okay, so you're gonna see me switch the notation on this problem. Be like, hey, College Board, I don't like your notation. Anyway, so that's one thing I'll do. You could do that if it helps you, or you could just use the spirit of what I'm saying to have it help you as well. So anyway, but you're just not going to see me use uppercase R, probably. Okay, so now let's talk about what is it that we want and what is it that we have. Okay. So what are they asking us for? They want to know an approximation for the number of liters of oil that are in the tank at time t equals 15 hours. So with my notation, that would mean they want to know the volume of oil that's in the tank when t equals 15. And they're saying it's okay to get an approximation as long as we do it a certain way. And then what is it that we have? Well, they gave us the initial condition that at t equals 4 hours. So the volume when t is 4 was 50 liters. And so this is one of those times where you want to know, kind of like a position function, essentially, or an amount function, but you have its derivative. And so we're just going to use an integral with strategically chosen bounds to get it. So, and then we'll worry about the Riemann sum garbage in just a second. So let's get our main idea set up, okay? So what would you have to do to dv dt to get v? That's right, you'd have to take its antiderivative. So I'll just move it over here. So we do the antiderivative of dv dt with respect to t. And then what bounds would make sense? So we would use t equals 4 and 15 for bounds, okay? And then the next step, it's up to you if you want to show it, but you could simply cancel the dt's out and you end up with the integral of 1 with respect to v. And then your bounds are t equals 4 and t equals 15. I'm saying t equals because otherwise it would kind of be assumed that they're v values. I hope that makes sense. Okay, so then antiderivative of 1 with respect to v would be just v. And then we'll plug the 15 and the 4 in. So we'd have the volume when t is 15. Take away the volume when t is 4. Okay, so what do I now know? I now know, and now I'm going to go ahead and replace dv dt with r of t, okay? I now know that the integral from 4 to 15 of r of t dt is exactly the volume when t is 15. Take away the volume when t is 4, but they gave us that was 50. So I'm just going to go ahead and put a 50 in right there. So hopefully everybody's okay with what I have here. And so the volume when t is 15 would just be whatever this integral equals plus 50, because you just add the 50 over. So the next thing, now this is when the Riemann sum piece comes in. We're going to use a Riemann sum to approximate this integral. And so if you need help with that part, one suggestion I always make for when they give information in table form would be to just do a quick sketch of what it looks like. And it's not an award-winning sketch because it's on your scratch paper and nobody but you probably will ever even look at it. So anyway, so you've got, you know, these uneven jumps, which some people thought that was a problem. It actually isn't. So you've got 4, you've got 7, you've got 12, and you've got 15. And then the rates at each time, dv/dt essentially, were 6.5, which I'll just like, this is a horrible notation, but you know, it's just for me anyway, right? 6.2, 5.9, and then 5.6. Okay, and there is likely some smooth rate function that connects these points, right? I don't know what it looks like. We'll never really know exactly what it looks like. But the point is that there is, let me get a highlighter. Okay, there is some perfect value of this integral out there that we will never find because we just don't have enough information to get it perfect. So that's why they're asking us to use a Riemann sum for it. So let's review what a right Riemann sum would be. So in this case, they said for 3, and you just use the natural spacing created by the time increments that they gave. So you'd have from 4 to 7 is one subinterval, 7 to 12 is another one, and 12 to 15 is the third one. And since they said a right Riemann sum, on every subinterval, you're going to use the height on the right. So you use 6.2 for the height of this rectangle. And then you just do base times height to get the area. And you can see that like there's some error between the area of the rectangle and the real integral most likely. But that's why we call it an approximation. So, and then the next one would be 5 at the bottom, and then times 5.9 since it's a right Riemann sum. And the next one is 3 at the bottom, and then times 5.6. And then you just add these 3 areas together, and that would be an approximation of what that actual integral value would be from 4 to 15. So we are approximating this by doing 3 times 6.2 plus 5 times 5.9 plus 3 times 5.6. And it's approximation for this, so it would be approximately equal to the right side. And then remind yourself, what are we finding? That's right, we're finding v of 15. So now it's just a matter of simplifying and then adding the 50 over, so no big deal. Let's see, 3 times, this is a non-calculator problem, mean 18 plus 0.6, so 18.6, 25 plus 4.5 for that one, 15 plus 1.8. I'm just going to add the 50 over. There we go. Oh, good times. Okay. Oh, I don't want to add these. Okay. 50. 65. 69. 70. 95. 105 plus 8. 113. 113 plus 1.1 and then 1.9. Okay, so what is that, 114.9? I would not be surprised if I'm messing this up. Arithmetic has not been my thing lately. Please let that be an option. Oh my goodness, it's an option. Okay, so either I got it right or I screwed it up just right. Anyway, all right, hopefully the answer is C. I'll check in a minute, redo this video if I need to. Anyway, but no, I think that's probably the answer. Anyway, so hopefully my explanation makes sense. it's a fundamental theorem of calculus move, which they're going to test you that in at least a couple of places, and then using the appropriate Riemann sum to approximate the value of the integral. That's really all it is. All it is to it. It just seemed like a lot though.